But everything else was just like, it was like 40, 48, 48, 50. No. I was lost stuff halfway through.
Because I tried typing in the answer he came up with and it said it was wrong. And now I just
We'll start in about a minute. We'll continue with test 3 review. On Friday, we'll have our test. You can join the Zoom meeting a few minutes before 9, and then you'll have until 10 o'clock to finish the test 3. I'll send the information tomorrow for the Zoom meeting. Continuing from where we left off yesterday. Let's sketch the polar curve r equals 1 plus 2 times sine of theta. So if we sketch the Cartesian graph first, so one period will be between 0 and 2 pi. So when theta is 0, r is 1. When theta is pi over 2, r is 3. When theta is pi, r is 1 again. And at 3 pi over 2, r is negative 1. And at 2 pi, r is 1. So the Cartesian graph looks something like this. So the r values are 0. Where? So that's 7 pi over 6 and 11 pi over 6. Just an observation. So when we sketch the polar curve, When theta is 0, the R value is 1. At theta equals pi over 2, the R value is 3. So the graph is doing something like this between 0 and pi over 2. Between pi over 2 and pi, it's symmetric. It goes back to 1. And then between pi and 7 pi over 6, between pi and 7 pi over 6, the R values go to 0. And then between 7 pi over 6 and 3 pi over 2, the R values are negative. And the R value is -1 at 3 pi over 2. So there's going to be an inner loop from 3 pi over 2 to 11 pi over 6. It's coming back around to 0. And then from 11 pi over 6 to 2 pi, it's going back to 1. So did anyone do that beforehand and discover that inner loop? Okay, let's move on to the next one. Let C be the curve defined by the equation x squared plus y squared quantity squared equals 2x squared minus 2y squared. Find the equation of the curve C in polar coordinates, and then find the total area bounded by C. Well, the x squared plus y squared is r squared. So we can write r squared squared. And up here, I'll just remind you what x is in polar coordinates. X is r cosine of theta, and y is r sine of theta. So 2x squared is going to be 2r squared cosine of theta squared. So 2r squared times cosine of theta squared. And then minus 2y squared, that's going to be minus 2r squared sine of theta squared. We can divide both sides by r squared to get rid of that extra r squared. And when we do that, we'll get r to the second equals 2 times cosine of theta squared minus 2 times sine of theta squared. Okay, what I'm going to do, I'm going to replace sine of theta squared with 1 minus cosine of theta squared. So we'll get r to the second equals 2 times cosine of theta squared minus 2 times the quantity 1 minus cosine of theta squared. So altogether, we're going to get 4 cosine of theta squared and then minus 2. So I'm skipping a step, but you can see when we multiply -2 times negative cosine of theta squared, we're going to get a total of 4 times cosine of theta squared and then minus 2. Are we all in agreement so far? Okay, since I First, when it says find the equation of C in polar coordinates, well, any one of these is okay, but since we want to find the total area bounded by C, I want to get it into a form that's easy to integrate. So I'm going to replace cosine of theta squared with 1/2 plus 1/2 times cosine of 2 theta. That's one of those identities that you really want to know if you're going to ever integrate cosine of theta squared. So cosine of theta squared is equal to 1/2 plus 1/2 times cosine of 2 theta. And then we have the -2 on the outside. So when we simplify a little bit further, we get r squared equals, so I'll just skip a step by just telling you what's going to happen. And you can see it, 4 times 1/2 is 2, and we have a -2, so those combine to make 0. And then we're just left with 4 times 1/2 cosine of 2 theta, or r squared equals 2 times cosine of 2 theta. Okay, it would probably be helpful to know what the graph of r squared equals 2 times cosine of 2 theta looks like. So what I'm going to do is I'm going to sketch the graph of r equals 2 times cosine of 2 theta. And then in the Cartesian plane. And then we remember that r squared equals that. So this is just the graph of r equals 2 times cosine of 2 theta. So there are 2 periods of that between 0 and 2 pi. So I'll try to squeeze those in. Oops, 2 pi. Okay, we start out when theta is 0, start out at 2. Maybe I'll use different color. Yeah, so this is the graph of r equals 2 times cosine of 2 theta. But the polar curve this just says r squared equals 2 cosine of 2 theta. So we have to only use the part of this graph where 2 cosine of 2 theta is positive, because r squared is never negative. Okay, so the interval between 0 and pi over 4 is non-negative. So when theta is 0, 2 cosine of 2 theta is equal to 2. So that means See, if r squared equals 2, then r is the square root of 2. See what I mean? We're sketching a graph of r squared equals 2 cosine of 2 theta. So when 2 cosine of 2 theta is equal to 2, r squared equals 2 means r is the square root of 2. And then when we get to pi over 4, the r value is 0, so r squared is 0 also. So we get this part of the loop. 2 cosine of 2 theta is negative between pi over 4 and 3 pi over 4. So we can't graph what r squared is on that interval because r squared is not negative. So we pick it up again at 3 pi over 4. Okay, 3 pi over 4 is right there. So we're starting out at 0, and then by the time we get to pi, the r value is 2. So if r squared is 2, r is square root of 2. So at the angle theta, we're right here. And then between pi and pi over 4, this is positive, so r squared goes from the square root of 2 to 0. And then we can't graph r squared for these negative values, and we pick it up again at 7 pi over 4, which is over here. The r value is 0. If r squared is 0, then r is 0. And then the r values are positive again, so at 2 pi, if r squared is 2, r is the square root of 2 again. So we get this sort of a loop. Notice what we can do. I don't really have a lot of room. I might be able to squeeze it in over here. If we go in the negative direction for theta, negative pi over 4, we can extend the graph of this in that direction. And so if we want to find the area that's enclosed by that curve, we can integrate between theta equals negative pi over 4 and theta equals pi over 4. If we do that, that will give us the area of this first loop, but the area of the second loop is the same as the area of the first loop. So we'll just multiply the integrand by 2. So the total area bounded by that entire curve will be equal to 2 times the integral from negative pi over 4 to pi over 4. And what's the formula for the integrand if you want to find the area of a polar curve? It's 1/2 r squared d theta, right? Well, r squared is 2 times cosine of 2 theta. So I'll write that out. 1/2 times r squared in this case is 1/2 times 2 cosine of 2 theta d theta. And then 1/2 times 2 is 1. So we just get the area equals 2 times the definite integral from negative pi over 4 to pi over 4. of cosine of 2 theta d theta. This is a pretty simple integral to evaluate. Let's just take it one step further and write down an antiderivative for cosine of 2 theta, which is 1/2 sine of 2 theta, right? And then we evaluate that between negative pi over 4 and pi over 4. So 2 times 1/2 is 1. So that reduces to a factor of 1. Sine of 2 times pi over 4. See, 2 times pi over 4 is pi over 2. Sine of pi over 2 is 1. And then we're subtracting sine of 2 times negative pi over 4. Sine of negative pi over 2 is negative 1. So 1 minus negative 1 is 2. Okay, so the area, the total area of that entire curve enclosed by that curve is 2. All right, let's move on to the next page. This time find the area of one loop of the polar curve r equals 2 times sine of 2 theta. So let's see, I was going to, oh yeah. We already graphed r equals sine of 2 theta. We did this graph yesterday. So if I wanted to graph r equals 2 times sine of 2 theta, I would just make these the length of these loops twice as long. So I want to use this graph from yesterday. If we want to find the area of one of those loops, we can just integrate from 0 to pi over 2. So if you remember, we got one of the loops between theta equals 0 and pi over 2. See what I mean? So on this one, we're going to find the area by integrating from 0 to pi over 2 of 1/2 r squared. This time r is 2 times sine of 2 theta, so r squared is 4 times sine of 2 theta squared. So we'll put that in there, 1/2 times 4 times sine of 2 theta squared. That's our area, or the value of this integral will be the area. Okay, what should we do? So sine of 2 theta squared, we'll use an identity for that, so we can integrate. Yeah, sine of 2 theta squared is 1/2 minus 1/2 of cosine 1/2. Okay, let me start over. Sine of 2 theta squared is equal to 1/2 minus 1/2 times cosine of 4 theta. We're doubling the angle. So in general, if you have, I'll just say sine of a squared. This is 1/2 minus 1/2 cosine of 2a. That's the one way to write that identity. I don't think I used a before, but this is the identity that we want. So in this case, the a value is 2 theta. Okay, so 1/2 times 4 is 2. And then replace sine of 2 theta squared with 1/2 minus 1/2 of cosine of 4 theta. So the resulting integrand is pretty simple to evaluate. So 2 times 1/2 is 1, and then 2 times minus 1/2 cosine of 4 theta is minus cosine of 4 theta d theta. Okay, so an antiderivative of 1 minus cosine of 4 theta with respect to theta is theta minus 1/4 sine of 4 theta. And we evaluate this between 0 and pi over 2. So you can see right away that there's only going to be one term. All of the other 3 terms are 0 when we evaluate this. So when theta is pi over 2, we get pi over 2 minus 1/4 times sine of 4 times pi over 2 is 2 pi. So this term is 0. Sine of 2 pi is 0. And then minus 0 minus 1/4 times sine of 0. So the only term that isn't 0 is pi over 2. So pi over 2 is the area of one loop of that polar curve. Okay, for this next problem, let C be the logarithmic spiral r equals e to the k theta, where k is a constant. I don't think I gave you enough room, at least for this first part. So I set aside a piece of scratch paper somewhere. So I'm going to rewrite this so that we have more room on another piece of paper. Okay. So we have this polar equation, r equals e to the k theta, and k is a non-zero constant. So maybe a little bit later we can sketch the polar curve, but for now we just want to find an equation of the line that's tangent to the curve at theta equals 0. So we use the fact that x equals r cosine of theta, but since r is e to the k theta, x is e to the k theta times cosine of theta. And y is equal to r times sine of theta, or e to the k theta times cosine of theta, times sine of theta. Okay. So if we want to find an equation of the line tangent to C at theta equals 0, we need to find the x and y coordinates of that point. So x is a function of theta. But we want to evaluate x when theta is 0. Gee whiz. I'll do it down here. X of 0 equals. Okay, replace theta with 0. We get e to the 0, which is 1, times cosine of 0 is 1. So the x coordinate of the point is 1. And y of 0, e to the 0 is 1, sine of 0 is 0, so y of 0 is 0. And so our x and y coordinates of the point are 1, 0. Okay, now we need to find the slope of the tangent line that passes through that point. So we want to know what dy dx is. Y is a function of theta, so that means we want dy d theta in the numerator and dx d theta in the denominator. So in the numerator, remember r is a function of theta, so we have a product of two functions of theta, y equals r times sine of theta. So the formula, we use the product rule to find the derivative of y with respect to theta. It's going to be the derivative of r with respect to theta times sine of theta plus r times the derivative of sine of theta with respect to theta, which is cosine of theta. And then in the denominator, since x is r times cosine of theta, the formula for the derivative is dr d theta times cosine of theta, and then minus r times sine of theta. Okay, but remember that r is e to the k theta, and so dr d theta is k times e to the k theta. Okay, so let's do the tedious thing in this formula for the derivative of y with respect to x. Replace dr d theta with k times e to the k theta, and replace r with e to the k theta. So our derivative with respect to x, derivative of y with respect to x, is k times e to the k theta times sine of theta plus e to the k theta times cosine of theta. And in the denominator, k times e to the k theta times cosine of theta minus e to the k theta times sine of theta. Okay, then evaluate this derivative when theta equals 0. So evaluate the derivative of y with respect to x when theta is 0. So in the numerator, when theta is 0, the sine of theta is 0, so this entire term is 0. And we get e to the 0 times cosine of 0 is 1. So the numerator is just 1. And in the denominator, k times e to the 0 times cosine of 0 is k times 1, or k. And we're subtracting e to the 0 times sine of 0, which is 0. So that's it, 1 over k. That's the slope of the tangent line that passes through the point 1, 0. Okay, so now we can just write down the tangent line equation. So the ordered pair is 1, 0. The slope is 1 over k. So we can write y minus 0 equals 1 over k times the quantity x minus 1. Or just y equals 1 over k times x minus 1. Okay, we'll go back to the other sheet. I'll write down what the slope of that, or what the equation of that tangent line is. So y equals 1 over k times x minus 1. And we can do part B on this. Find the length of the curve C for values of theta between 0 and 2 pi. So the arc length formula for polar curves. Square root of something.
dx over d theta squared plus dy over d theta squared.
Yeah, or in this case, we can just write it as the square root of r squared plus dr d theta squared. Okay, so we have r, and we know what dr d theta is. So up here, I'll just write what r squared is. Since r is e to the k theta, r squared can be written as e to the 2k theta. And dr d theta is just k times e to the k theta. So when we square that, we get k to the second times e to the 2k theta. So we add those and put them inside the square root. So between 0 and 2 pi, so e to the 2k theta plus k squared times e to the 2k theta. Theta, each of the two terms inside the square root have e to the 2k theta. So if we factor e to the 2k theta out of each of those and then take the square root of it, we'll just have e to the k theta outside of the square root. And inside the square root, we have 1 plus k squared. You see that, or you want me to go into more detail on that one? Okay, the square root of 1 plus k squared is just a constant. And then an antiderivative of e to the k theta with respect to theta is 1 over k times e to the k theta. So 1 over k times the square root of 1 plus k squared. So that's just a constant multiple. I'll put that out, put that on the left. Square root of 1 plus k squared over k. And then we evaluate e to the k theta between theta equals 0 and 2 pi. So the square root of 1 plus k squared over k, then e to the 2 pi k minus e to the 0, which is just 1. So that is the arc length. Okay, the next one, write the first 4 terms of the following sequences. Indicate which ones converge. So 5 to the 1 over n, as n ranges from 1 to infinity. So the first term is 5, then 5 to the 1/2, then 5 to the 1/3, and 5 to the 1/4, and so on. So do you think that sequence converges? So this is one of those where you can maneuver the limit. You have the limit as n approaches infinity of a constant 5 to the 1 over n. So we can write this as 5 raised to the limit as n approaches infinity of 1 over n. And as n approaches infinity, what does 1 over n approach? 0. So we get 5 to the 0 or 1. So the limit of that is 1. Okay, the next one, this is just sort of an exercise of endurance, of tediousness. The first 4 terms, when n is 1, 1 minus 1 is 0. When n is 2, 2 minus 1/2 is 3/2. When n is 3, 3 minus 1/3 is 8/3. When n is 4, 4 minus 1/4 is 15/4, and so on. So does that sequence converge? Well, just look at the first term. Even though 1 over n goes to 0, as n approaches infinity, n approaches infinity. So this one diverges to infinity. Okay, then the next one, when n is 1, 1 plus 1 squared is 4 minus 1 is 3, 3 over 1, so 3. Then when n is 2, 2 plus 1 is 3, 3 squared is 9, 9 minus 1 is 8, 8 divided by 2 is 4. When n is 3, 3 plus 1 is 4, 4 squared is 16, 16 minus 1 is 15, 15 divided by 3 is 5. So this sequence is just a fancy way of incrementing the positive integers by 1 starting at 3. You could simplify that algebraically and it would become more apparent what the sequence does, but this one diverges to infinity. Yes, so if you haven't already done that, go ahead and simplify that expression and it will be more obvious that it diverges. Okay, for the next ones, write the following series using sigma notation. So this first one, 1/2 minus 1/4 plus 1/6 minus 1/8. If we start at n equals 1 and go to infinity, since the terms alternate, positive, negative, the first term is positive, so write -1 to the n minus 1. And then it looks like 1 over what? Yeah, 1 over 2n. And you can verify that just by testing the first few integers. Okay, the next one. Let's start with n equals 1 and go to infinity. Well, the numerator is always 1. The first term, the first factor in each of those rational expressions, they just increase by 1 each time, 2, 3, 4, 5. So if we start at n equals 1, that first factor is just n plus 1, right? And what do the second factors do? 3, 5, 7, 9. Those are just the odd integers. So if we start at n equals 1, 3 is 2 times 1 plus 1. At n equals 2, 2 times 2 plus 1 is 5. So it looks like this other factor is just 2n plus 1. See how that works? Okay, on the next page, we'll evaluate a series. Evaluate the series 5 minus 10/3 plus 29ths minus 40 27ths. This is a geometric sequence. You can find the common ratio if you divide a term in the sequence by the one that comes before it. So this just simplifies to -2/3. That's the common ratio. You can find the same number if you divide 29ths by -10/3, and so on. So we know that it converges. How do we determine what it converges to? Well, we can put it into this form. The series where n starts at 1 and goes to infinity of 5 times the common ratio, -2/3, to the n minus 1. So when n is 1, n minus 1 is 0, and -2/3 to the 0 is 1. 5 times 1 is 5. When n is 2, 2 minus 1 is 1, and 5 times -2/3 is -10/3. So it appears that this is the appropriate form to write it in. And this is in the form, the geometric series form of a times r to the n minus 1. And since r is between -1 and +1, this formula says the sum is a divided by 1 minus r. So for this one, the value of a is 5. R is -2/3, so 1 minus -2/3. And 1 minus -2/3 is +5/3. And 5 divided by 5/3 is equal to 3. +3. So this series converges to +3. Okay, on the next one, have you done this one? Find the sum of the series or show that it diverges. Since the terms of the series are 1 divided by n times n plus 1, hopefully partial fractions will come to mind. And since we're down to a little bit more than 2 minutes, if you find the values of a over n plus b over n plus 1, it turns out that a is positive 1 and b is negative 1. So you can rewrite this series as the terms being 1 over n minus 1 over n plus 1. And then if you find the first few terms in this sum, when n is 1, we get 1 minus 1/2. Then when n is 2, we get 1/2 quantity 1/2 minus 1/3. Then when n is 3, we get the quantity 1/3 minus 1/4. When n is 4, we get the quantity 1/4 minus 1/5, and so on. This is called a telescoping series. So minus 1/2 plus 1/2, those cancel each other out. Minus 1/3 plus 1/3, minus 1/4 plus 1/4, and so on forever. So the series converges to the only number that survives. In this case, it's 1. So that's the value of the series. The next one is a geometric sequence. We're out of time. So this one, check to see if it converges. I should say it's a geometric series. If it converges, it means the common ratio is between -1 and +1. If it's something other than that, then it's diverges. And then, even though we're over time, I want you to make sure to use the test for divergence for this series. Since the limit of the terms does not equal 0, then the series diverges according to the test for divergence. So in the textbook, if you haven't read that test for divergence, then make sure you do that. Okay, that's all for today. The test is on Friday.